let's start out looking at some of the basic things we're going to need to know. All right, so we're going to look at a few vocabulary terms, and as we go through them, we'll do some examples with you guys. Make that a little bigger. All right, so we're going to see kind of what you guys already know. Okay, just read that first sentence. It says, a blank is a symbol used to represent an unknown quantity. Anybody know what we use in math to represent something we don't know? An unknown.
Is that
Yeah, go ahead, Gabe.
Like a X or a Y.
Yep, those are good. Those are two examples of what this thing is called. An X, a Y, basically any letter. Yep, Sam?
A variable.
A variable, good. Okay, a variable. Okay, so a couple people already gave some examples. X, Y. A lot of times we use those when we're graphing. M. Mr. Roy mentioned something about point slope or slope-intercept form earlier. You might see letter M when we do stuff with that.
So guys, like a general term for a variable. What's a variable? I know it's like X, Y, M, Z, but when it comes right down to it, what's a variable?
Letter.
A letter, right? A variable is a letter. So we might say we might put in the notes like variable. We might put in parentheses the first 2 weeks letters so everybody knows. But it seems like everybody's got a pretty good understanding of what a variable is. They're going to show up now from the end of the school year.
All right, next one, it's a little bit tricky. Okay, I'm going to help you guys out with the second word. Second word is expression. Okay, the first word, what class are we in right now? Algebra, right? Algebraic. Okay, that's the first word here. Algebraic. Okay, so an algebraic expression contains one or more variables, or as Mr. White said, just one or more letters, and one or more operations. What are operations in math? We have 4 basic ones. First 4 you ever learn in math, yeah?
Addition, subtraction, multiplication, division.
Right, okay, so we're looking at something that it's got a letter in it, and maybe plus something. So anybody give us an example of an algebraic expression? So just say a letter, one of the 4 operations, and then maybe another letter, or you could pick a number. Yeah.
6x plus 5.
Perfect. Nope, no equals yet.
Oh, yeah.
Once we throw an equals in there, that's going to become something else. But 6x plus 5, perfect. Okay. Even just a letter by itself, x. Okay. 2x. What operation is that? When you have a number right next to a letter. Yeah?
Multiplication.
Good job, Caitlin. Okay, good. Multiplication.
And guys, just moving ahead. So if I had something like that, right? If I had that 2x, and I needed maybe to like cancel it out, get rid of it, get it by itself. All right, somebody besides Gage and Sam, thank you guys, but I want to hear from somebody else. What do you think? Is it hold on? Is it Ariana?
No.
What is it? Sabrina. I was close to it. I look the same letter. Sabrina, what do you call that? What would you do?
Divide by 2.
Yeah, you would divide, right? When you want to get rid of multiplication, always divide by the number that's attached to it. And we're gonna give a fancy term for that number attached to a variable near the end of the notes. But if you want to get rid of something in math, and I think you guys seem like you pretty much know this, always do the opposite. Always do the opposite operation. We're gonna get into that next week.
All right, so the next one. Let's look at this. Let's fill in this word. It says to blank and blank. We replace or plug in each variable or each letter with a number. You ever know, what do you call that when you take a number and plug it in for a variable? The second word here we've already seen today. It's one of the words we used up above. This first word is a new word. You think they know? Yeah, go ahead.
Substitute is one of them, right?
Okay, substitute.
It's on the right track.
Could use that word, but yeah, we use a little bit different word here. Okay, when you plug in a number for a letter and then you simplify it and get an answer, we call that evaluating. or evaluate. And what are we going to be evaluating? Some type of expression. I think we have our first example we'll do. Okay, so anytime you see the words evaluate in directions, that's usually going to mean find the number. Okay? Your final answer should just be a number, like 5, 12, -8. Okay? Let me show you an example of what that looks like.
And guys, you have that example written right down in your notes.
Mr. Roy, they get that chart that's coming up next too already?
Yeah, all written out. The only thing we have to add is just the one trick about subtraction.
All right, let's look at what this one says. Evaluate 2 times x times y. What's the first thing you have to do if you're going to evaluate that? Before we can even start doing times, what do we got to do first? About Brian? What does it say to do on this step right here? How do you evaluate an expression? Plug in what? Plug in a value? Okay. How do I know what to plug in? Like, say, what am I going to plug in for x? Anyone help them out? Does it say anything up there? Is x supposed to be any kind of number, Ryan?
4.
Yeah. So x is 4. Okay. What about for y? What are we going to plug in for that? Yep, Maria? 3. That's the very first step to evaluate. Take all the letters, replace them with numbers.
For Mr. Hager to make that problem look, when he rewrites it, because now he's going to plug in those values that it told us because they're giving them to us, what can he use to make it look a little bit neater? So it's not all bunched up like 3 numbers all together. Anybody know? Justin, what do you think? What do you think you would use to kind of separate everything so it's a little bit easier to read?
Parentheses?
Yeah, exactly. What's he going to put parentheses around?
The X and Y.
What's taking the place of those things now? What numbers? Huh? 4 and 3, right? Exactly. Now, when Mr. Hager goes to solve this, does it matter the order that he does it in? Does it matter how he starts? What do you think, Sam?
In this case, no, but usually we do the parentheses first.
Why doesn't it matter what order he does it in?
Because you get the same answer.
And what else, though? Something else. Yeah. So we're going to talk about that a little bit later. But what's the only operation he's doing then? It's all multiplication, right? He can do it any way he wants. When it's all the same operation, it doesn't matter how you go about it. Maybe do the smaller numbers first, so it gives you a little bit something easier to work with.
So as Mr. Wright just said, I picked the first 2. 2 times 4, it's 8. And 8 times 3 gives me 24. Had you done it a different way, if you did 4 times 3 first, you get 12. And then 12 times 2 is also 24. Okay? So when you have all multiplication, you can do it in any order. Yep, same thing. We'll talk more about PEMDAS. Somebody said that earlier. Yep. All right, the next part you guys already have written down. These are basically some keywords that when you see them, it's going to tell you what operation it is. So the first one is plus, okay, or addition. Anytime you see the word plus, added to, increased by, more than, some, those aren't all the words, but those are a lot of them. Every one of those words in bold means addition. Okay? They all mean addition. Okay? So sometimes when you have a word problem, you've got to read the word and figure out what is it. Is it addition, subtraction, multiplication, or division? So we're just showing you the key words.
Because
Yep.
usually in word problems, they don't actually tell you they have those words in there, so you know that you have to add.
Yeah, a lot of times these are pretty straightforward. Yeah. How about, you guys already have this on your sheet, right?
Yeah, the last one there, the sum of, that's the one we do get into word problems, that's the one that shows up a lot. Alright? Sum means, sum, S-U-M, always means adding. Always, always, always. So that's why it's going to be good to have, when we get into word problems in a couple weeks, it's going to be good to have this chart, because this go back, if you're not sure, look back, and know what it means.
Okay, these are some words that you're going to see with subtraction. Okay, when word problems come up, you might see the word minus, subtracted, okay, less than, okay, difference, or decreased by. Okay, now Mr. Roy writes something here. Order matters, specifically with this one. For example, if I said to you, let me just write this out, 3 less than 10. Actually, you know what? It's actually this one. Backwards. That's the one you're going to be careful with. How would you write that out? If I said, type that into a calculator, 3 less than 10. Think about in your head what the answer should be. 3 less than 10. And how you type that in on a calculator. Caitlin?
10 minus 3.
10 minus 3. Notice what happened here? You don't put 3 minus 10. The order gets switched. So that's something when you see the words less than, the order matters. You always write the second thing first. So how about this one? X less than 42. How would you do that? If I said type that in on a calculator. Think about it the same way we did this one. X less than 42. Just changing those two things. Yep.
42 minus x.
Perfect. 42 minus x. This is the one that always trips people up.
Yeah, guys, but it's gonna again, something else that's gonna show up all year long. You gotta know when it's less than. Whatever comes after that less than is gonna go first. Put your minus sign, and then put the first thing that's mentioned. All right. A lot of kids get tricked on that. That's why we want to talk about it early on.
A lot of these other ones are straightforward. 42 minus x. That would be the way you see it. The difference of 42 and x, you wouldn't have to do anything. 42 decreased by x. X subtracted from 42. Those two I circled, that would also be backwards.
I'm gonna say, would you agree that when we're doing like word problems and stuff like that, that less than is usually the one that shows up the most, right? Usually,
Yeah.
you can get that one quite a bit.
Difference or less than, we see
Yeah.
those a lot. The difference of two numbers is something, yeah. Right, so the next one, all different words you're going to see for multiplication. Times, multiplied by, product. The word of. Okay, if you see the word of in math, a lot of time that means multiplication. Like if I said I wanted half of the students in here. Okay, I want to know half of the students. I'd take how many I have times 1/2. Half of the number of students.
You guys, the times, the first one has 16 times x. That's the one we're doing. When we move on, that's the one that shows up a lot. A lot of the times that's so whatever number it is, take that number and put a variable with it. So if it was like Dad, if it was like 4 times something, how would you represent it? How would you show it? If you had to write it out, it said 4 times and 4 times some unknown. How would you write that out? It would be 4 what?
4x.
4x, right? 5 times something. How would we show it? Yes. 5x, right? Don't get. I know from working with kids in the past, they get tricked on that. It's kind of like it's gonna be more to it than that. It's gonna be. I gotta do something more. It's that simple. 4x, 5x, 6x. It's that simple. All right. Don't get tricked on that one. All right. You don't need any more than that.
And then the last basic operation we have is division. So you might see divided by. Quotient, that's one sometimes people forget. How many people already knew that one before today? If I said the quotient of two numbers, they know what means divide. Okay. Well, if you didn't, now you know. Quotient means divide. All right, so we're going to look at a couple of these sentences and just see if we can figure out how to find the keywords here and change it into an algebraic expression. So we're going to have letters, we're going to have numbers, and we're going to have an operation, maybe add, subtract, multiply, or divide. All right. Now, in the first one, they picked the letter for us. If they didn't, we'd be picking it. Right? But they're telling us what letter to use. What letter do they want us to use for part A? Yeah, Gabe?
P.
P. The cost of P pounds of tomatoes at 79 cents per
So
pound.
guys, you don't have that example written out, so you're gonna need to write it out on your sheet. You have a spot for example A, you just have to write it in there.
Okay, as you look at that, does anybody see a word in here that tells us what operation we might be doing? Add, subtract, multiply, or divide? Yeah? Of, perfect. That word of right there is telling us we're going to do something with multiplication. Okay, so as we said earlier, we could use parentheses. In this case, we might not need parentheses. We'll see what happens.
So guys, when Mr. Hager's doing this, what's the first thing he's gonna write?
79.
Right? 79, right? Then, after that, what's he gonna write? What do you think?
X.
P.
P.
Ben, do you agree, Ben? They're gonna write P? Right, good. Whenever we're dealing with multiplication, take the number, put the variable next to it. All right, take whatever number they give you, the variable next to it. In this case, it gives you the variable, it tells you to use P, so obviously use P.
And that's it. Did anybody write it with parentheses? Anybody put parentheses around it? You could.
You're not wrong.
If you did something like this, that's exactly the same thing.
Mr. Hager, would the other way be okay? 79 with parentheses and a P?
Yep, you could do it that way. All those ways are correct. Right?
Even if I'm not gonna make Mr. Hager do it, what else could he have used there instead of parentheses? What's another way that multiplication is represented? Yeah, Gage is right. You could have put the little dot. You could have put again. When we're doing multiplication, guys, it wouldn't be a good idea to use like the x, like the times x. Why would that be a bad idea? Again, exactly. If you're dealing with variables, right? You have an x as a variable. You might get confused and do something that you're not supposed to. So probably the best way is just write the number and the variable side by side.
And the decimal, I heard, or not decimal, the dot, somebody said that's perfect. That would work great here. The only time I would stay away from the dot is when you have numbers with decimals. Like if I had, say, 1.2 times 4.3, that kind of looks a little confusing. People agree? Like if I had to do something like that, I think the parentheses might make it look a little cleaner. All right? But otherwise, the dot is fine to use as long as it doesn't look confusing. Yep. Okay, next one. Y years less than
This
X
challenge,
years.
Mr. Hager, is a tough one.
And if you get confused by the word years, just pretend it says Y less than X. Whether we're talking about years, tomatoes, whatever. Y less than X. I think we did an example, 3 less than 10. That's the one I gave you earlier.
Has anybody we haven't heard from yet think they might know this? You know? Ooh, x minus y. Everybody agree? Everybody agree? So what's the key, Samantha? What's the key word there that we know it's going to be, or the key phrase that we know that it's going to be subtraction?
Less.
Perfect, less than. And what's the trick when it's less than? You can tell me. Ryan, what's the trick?
Subtract.
I agree with that. But why couldn't I go y minus x?
It's because it's the opposite.
Exactly. That's it. When it's less than, that's the tricky one, right? Reverse the order, switch them around. All right. Put the second thing first. I know it sounds weird, and kind of funky. That's just the way it is. That's just the way it is. Gage, question?
That's what I'm trying to do. Is
Oh, believe me, I've seen it. I've seen it 100 times. That's why I'm stressing it so much, because it shows up all the time. We hate to take points off on tests. You don't set it up right.
Okay, how about the last one? X increased by 14. And there's a couple ways you could do this one and be right. You're less likely to make a mistake with this one, especially with order. Justin?
X plus 14.
Yeah. Now, what if he said 14 plus x? Same thing, or is that different?
Same thing.
Yeah. When you're adding numbers, the order you add them in doesn't matter.
Yeah.
2 plus 3, 3 plus 2, you get 5 both ways.
Because if either way, guys, both, whatever it's giving you as a variable or whatever, they're both gonna be positive, all right? Because it's a big thing, even though that first term, that x, that variable, doesn't have a sign with it, if there's no sign to the left of it, we assume that's positive. This is the way it is. That's just the way it works, all right?
They got a second page, Mr. Ward?
Flip it over, Mr. David.
Like somebody earlier, I think you guys jumped a little bit ahead, you probably already know this.
Mr. David.
Gauge,
Oh, yeah.
you already know this. So when we do arithmetic, there's a certain order we have to do it in, okay? And that order guarantees that we're all doing it the same way, we're all going to get the right answer if we do it correct. Right? And Gage, what did you say that word was?
Wait. Yeah. Substitution.
No, you
PEMDAS.
got it right, man. Be
PEMDAS. So
Got it.
PEMDAS is an acronym that we use to remember the order.
Hey guys, when I say that word acronym, does everybody understand what that means? Huh? You know what an acronym is? What do you think, Dustin?
It's like, it's hard to explain. It's like when you give an initial to the first letter.
Yeah, every letter like stands for something.
Yeah.
All right, like NBA, like National Basketball Association, NFL, National Football League,
Scuba,
scuba. I don't know what that
self-contained underwater breathing apparatus. Wait.
USMC, United States Marine Corps. So those are all examples of acronyms. So we use the acronym PEMDAS. Each letter means something. We're going to go through that right now and tell you what each letter means.
Anybody think they know? Gage, I know you know.
I do know.
Anybody else know what the first?
Redeem myself.
Oh.
No.
I think I do.
Now Garrett wants to get involved.
I know.
Yeah?
Yeah.
All right, go ahead. Yeah, go ahead.
Parentheses.
Parentheses.
Nice.
All right, so we got parentheses. What else? How about the E? Yep, Michaela?
Sorry, exponents.
Exponents. Okay, what about the M? Yeah, Gabe? Multiplication, good. Multiplication. About the D? Caitlin?
Divide.
Yep, divide or division. And last two. About them?
Addition.
Addition. And last one, yep, Samantha? Subtraction. Okay. So this is the general order that we do everything in. Okay? Does anybody know parentheses? Those are called a grouping symbol. Does anybody know another symbol you might see besides parentheses?
Is it like a straight line?
Brackets.
You could see brackets, so it's definitely possible you've got something like this.
I don't know the name.
Okay? You can use brackets, parentheses, it's the same thing.
They do what's inside of whatever that grouping symbol is, do whatever in there first.
Yep.
Okay.
Sometimes we even see like a fraction bar. Okay? You could have a problem like this. 4 minus 2 over 5 plus 3. What you do with that is, whenever I see a fraction bar, I always do the top first, and then I do the bottom. Okay? So that's the fraction bar is like a grouping symbol as well. It tells you do the top part first, then do the bottom part. Okay?
And Mr. Hager mentions fraction bar. What, with a fraction, right? What that bar, what math operation is that representing? Sam?
Division.
Division, right? So keep that, that's another big one as the year goes on, all right? Remember, any fraction bar, any fraction is really a division problem, all right? You can always make that fraction into a decimal or a number, right? It's always divide the top number by the bottom number, all right?
Okay, and then multiplication and division. Multiplication isn't always before a division. That's how we write it, but it's done in order from left to right. Okay, let me show you an example. 4 divided by 2 times 3. In that case, you would do 4 divided by 2 first. Okay? You always just do your division and multiplication in order as you see it, left to right. Okay? You wouldn't do like 2 times 3 or anything like that. You do 4 divided by 2 and then times 3. What would that come out to?
2.
Yeah. 4 divided by 2, that's 2. Good. And then
What
2
if there's
times,
like 1 over 5 times 3? You wouldn't get
and then that'd be
divided.
6. Yep. What if you had, go ahead, give me another one.
1 over 5 times 3?
1 over 5 times 3.
You'd have to put the 3 over 1. Right?
Yeah, perfect. You could put the 3 over 1. And now, Mr. Roy mentioned earlier, if you can divide them and reduce it, you do. In this case, does 1 divide by 5 reduce? No. So you did it perfect, and then you multiply straight across. 1 times 3, 5 times 1. 3/5, that's all you could do. And if we asked you to change to a decimal, you could use a calculator.
And guys, Sam makes a really good point there, because there'll be times where we get the stuff as we move on. You might have a fraction, but the other number is a whole number. And Sam made a good point of any whole number can be put over 1. Any whole number can be put over 1. We just don't. It would take so much time to write every whole number as a fraction over 1. You just have to imagine that it's over 1, right? Just like any whole number, if I had, 1005, it's always to, when we talk about exponents, it's always to the first power. We just don't write. It's assumed. It's the way math works.
Anybody have any questions on PEMDAS? Okay, let's try it. What do we have for grouping symbols there? It's one thing we have. Yep, Caitlin?
The fraction.
Yep, we got the fraction bar, so that tells us maybe we'll work on the top first, then we'll work on the bottom. And what else? Yeah, Gage? We also have parentheses. All right, so, there's a couple different orders you can do it in, but we'll just try to go through it as easy as we can. Let's start with what's in the top, simplify what we can following our rules. And then we'll worry about the bottom as a separate problem. What can I do in the top? Do I do addition? I see that. Or do I do exponents? I see both. Alexis? Yeah, we got to do the exponents first. Do you know what 2 to the 3rd power is? 2 times 2 times 2?
8.
8. Yep, 2 times 2 is
Sorry, I
4.
raised my hand.
Times 2 is 8.
Remember, guys, don't make that mistake. It's not 2 times 3, all right? It's the bigger number multiplied however many times the smaller number says, all right? So in this case, the smaller thing is telling the bigger thing what to do, all right? Multiply that big number 3 times. 2 times 2 times 2. A lot of people make a mistake of doing 2 times 3. It's not that.
Okay, Ryan, how about the second one?
16.
Good. 4 to the 2nd power, or 4 squared, could also say 16. Okay, so we've done a little bit of work in the top. What about in the bottom? Do I do this exponent first? No, why not?
Because the parentheses are part of it.
Yep, we got these parentheses, so we've got to do what's in there. What is 5 minus 3, Gabe?
2.
2? Anything else I still have in the bottom? Well, we did those, right? So parentheses are gone
No,
now.
I need the exponent.
Yeah, the exponent. Okay, what can I do next? Oh, Corey? What can I do next?
Isn't it the bottom, which is the exponents first, or is it the top first?
These are, you could think of these as 2 separate problems. I would just do the top first. 8 plus 16, which is how much?
I didn't do that in my head.
24, good. Okay, top is done, that's it. Nothing else we can do in the top till we finish the bottom. Okay, what about the bottom? 2 to the second power. Yep, Gage? 4. Okay, what did Mr. Rice say about this? What can we do here? Yeah, go ahead, Maria. We can simplify it. What is 24 divided by 4? Or I think 4 times what gives you 24? 4 times 4 is 16. 4 times 8 is 32. So we're right around the number.
7?
4 times 7, 28.
26.
4 times 6 is 24. So we reduced it as much as we could, and we're done.
You guys see how the number on the top is bigger than the number on the bottom? Always check to see if that number on the bottom can go in even with that number on the top, right?
Okay, evaluate. So we've got exponents, we've got addition, subtraction, maybe some stuff with order of operations, but what's the first thing you have to do when you see the word evaluate? Well, Victor? What's the first thing we have to do when we see the word evaluate? Well, it's telling me to change something, right?
Yeah, I want you to plug in the X for 4.
Yeah, they want me to plug in 4 everywhere I see an X. Okay, so that's the very first thing I'm going to do. So instead of 3x squared, I'm going to have 3 times 4 squared. Okay? Minus 2 times 4 plus 1. Okay, order of operations. How about, Ariana, what would I do next here?
You multiplied 3 times 4.
Multiply 3 times 4. Everyone agree with that? Is there anything we can do before multiplication? We're going to do multiplication, but, yeah? Yeah, the exponent. Okay, 4 to the second power gives me 16. Okay, and I'll just copy the rest of it down. Some of you might do more than one step. Okay, but we'll just do one step at a time to keep it simple. Okay, 3 times 16. Anybody know what that is? If not, we can just use our calculator. Yeah? Good, 48. 2 times 4, that's 8. And then plus 1. Okay, what do I do next?
48 minus 8.
Right, we always do addition and subtraction in order, left to right. So 48 minus 8 leaves me with 40, plus 1 more, 41. Okay, so that's an example that had a lot of different steps of PEMDAS in it. Exponents, multiplication, add, subtract. No parentheses that time.
Alright, you guys have that written down on your notes.
Okay, how many people have seen that before, distributive property? Yeah, most people are familiar with it. So the idea with distributive property, it's multiplication. Usually multiplication to 2 or more things. Okay, and as it says right here, you take the number on the outside, and you multiply it to each number on the inside. Okay, a lot of times, Mr. Roy and I will draw those lines so you can see it. Okay, and we keep the sign the same. Whatever sign is attached to the left of that number, we'll keep it the same. Right, so we're going to simplify that. Basically, I already drew in the lines, but who can tell me what's the first thing I'm going to do using distributive property? Yeah, I heard someone say it. Yeah? 7 times 8. This could be a case if you want to use the dot. It's a good time to use it. Plus, keep that the same. Okay, what comes next? Yeah, 7 times 5.
You guys, Mr. Hager's just showing you, he's just writing out how it works, right? You don't have to do that, right? We're just showing you because it's the first time we're going over it. You don't have to write like 7 times 8 plus 7 times 5. We get it in distributive property. He's just showing you how it works so you can see it.
Most of the time when I do distributive property, I would have jumped right to this step.
Yep.
7 times 8 is 56. Plus 7 times 5 is 35. And we add those up. If I did that right, we should get 91. Okay, any questions on that one? So that's very basic distributive property. Just multiplying that out. All right, and I think we're getting towards, almost towards the end here. So last thing is a few different terms, okay? The parts of an expression that are connected by addition or subtraction signs are called, anybody know? And actually the word is on the board there somewhere. Like if I had something like 3x plus 2 minus 4y, there's 3 blank. That's the word I'm looking for. What are each of these things called? In the school year, there's 4 of them. Terms. Yeah. Okay, so the parts of an expression that are connected by addition and subtraction sign are called terms. Now, 18, there's no letter. 2, there's no letter. Does anybody know what you call a term that stays the same?
Yes.
What do you call it? Because we call something a variable because it can change.
Yeah.
Like if we say the weather is variable, we mean the weather is changing. What word do we use when it stays the same?
That's what we did last year.
Anybody know what word you use? Yeah?
Start-
All right, this is an example of an integer.
Starts with a C, right, Mr. Hager?
Yep.
Wait.
You got a guess? No? Constant.
Jill, you think you know?
Oh, I know that.
She's like, I don't know.
Yeah. Constant.
If something's constant, if you're consistent, it never changes.
Okay, so we call it a constant term or just a constant. Okay, so a number is a constant because there's no letter that never changes. The number 5 is always the number 5.
So you just want to write some examples of like terms, or you going to do the definition?
I'll put it down because it's quick, yeah. Okay, like terms. Okay, like terms are important to know because anytime you want to start adding and subtracting things, you can only combine things that are like terms. So I'm going to put down the definition, it's just one sentence, and then see if you guys can give me an example. So like terms have the same variables. And the corresponding variables have the same exponents. So corresponding variables have same exponents. Who can give me an example of a like term? Well, you know what? Somebody just give me a term, and then I'll ask somebody else to give me a like term that goes with it. How about Alex? Give me a term. Make sure it has a number and a letter in it.
3x.
3x. Perfect. Okay, so here's an example. Somebody give me a like term that would go with 3x. Yep, Jalen?
4x.
4x, perfect. Has the same variables, x and x, and each variable has the same exponent. Okay, Mr. Roy already said this, but what's the exponent here if it's not written on each x?
1.
It's a 1. Yep. Okay, let me give you guys a term. 2xy squared.
4xy squared.
4xy squared.
I was gonna say cube, but that would be unlike terms.
That would be unlike terms. Yep. So as long as you have the same variables. I think I wrote cubed and you said squared. I got confused. How about this one? 5x squared y and negative 2y x squared.
No.
Well, do they have the same variables?
Yes.
Yep. Is each variable raised to the same power? Is the power on the x the same on each side? Is the power on the y the same on each side?
What?
Is the power on y the same on each side? What's the power here?
Oh, yeah, yeah.
1 and 1. These are like terms. They're written in a different order. Probably not the best way to do it, but same letters, same exponents. Okay? Much better to write it in the same order, though. Okay? But those are all like terms. How about 2? What would be a like term with 2?
4.
4. Constant, constant. Okay? Like terms. Okay, and then somebody give me an example of unlike terms. We don't need a definition. We already have it up above. You could just say they do not have the same variables or they don't have the same exponents. How about Ryan? Can you give me an example of give me a term.
5.
5? Okay. And somebody give me something that's not a like term with 5. Yeah, Logan?
The variable z.
Sure, z. You cannot combine a number with a letter with addition. Can't do it. How about 2x? Somebody give me a term that you could not combine with 2x because it's not a like term. Yeah,
2y.
2y. Okay, part of it's the same, right? It's got a constant, you've got a constant, but one's an x, one's a y. You could not add those or subtract them. Okay, they're not like terms. Okay, here's one that you might look at quickly and it looks a little tricky. Let's say 3xy squared and 2x squared y. Those almost look like terms, but what's wrong? They got the same letters. Alexis?
The x and y are switched. And look at the exponents.
Yeah. The exponent on y is a 2, and on the right it's a 1. Okay, so and on the x here it's a 1, and on here it's a 2. So they're almost, but not quite the same. Okay, and this is the last thing, right, Mr. Roy?
That's it.
Okay. In the term 7x, okay, the number 7, that's out in front. Okay, we have a name that when you have a number in front of a letter. Does anybody know what that's called? When you have a number in front of a letter. I can't really think of a hint.
Yeah.
All right. The second part of this word. What do you call somebody who can do something very quickly? They're very good at what they do.
Someone's very good at their job.
They're very good. They don't waste any time. They're very...
Multitasker?
Okay, somebody who multitasks.
They get their work done quick. It's always done on time. You know? What do you think?
They're faster than everybody else at it because...
A good employee?
We got it?
Proficient.
Oh, close. I thought you said. Very
Just
close.
take off the first 3 letters of what you said.
Efficient.
Efficient. Okay, that's the second part of the word I'm thinking of.
Coefficient.
Oh, it worked, Mr. Roy. We got it. Coefficient. Perfect. So that's. Let's see. I think we got that. Yeah. Coefficient. Okay. Anytime you have a number in front of a letter, like there, that's called a coefficient. 2xy. 2 is a coefficient. Okay? And this part we stressed earlier, only like terms can be added or subtracted. Okay? So none of these three things, if I asked you to add or subtract, can't do it. All of these could be added and subtracted. 3x plus 4x would be 7x. We'll talk, I think, more about that in chapter 2. Okay. Any questions on that? All right, so tonight, Mr. White, what are we going to do? We're going to...
Guys, tonight, well, just a couple reminders, so you guys know. Number one, you guys doing a pretty good job with this, getting those forms signed. We had quite a few back today, especially Mr. Hager's form, right, for the class. Make sure you get that signed. Guys, homework this weekend. The thing Mr. Hager gave you yesterday, the daily motion. Go on there, all right? At the end of the notes from today, there's going to be 5 or 6 questions that are going to deal with combining like terms. All right, so sometime this weekend, or if you have learning support or something like that, directed study, get yourself on a computer, go on the daily motion so you can get used to using it, right, Sam? So you can get used to using it, get logged on, see how it works, get yourself on there, and there'll be like 5 or 6 questions that deal with combining like terms on there. All right, so check that stuff out.